Hi, it's Dr. Khan with the last sections of Chapter 16. We'll be talking about weather data. Here are the learning objectives for these sections. First, we're going to talk about air temperature data, and there's a lot of different ways that we can take air temperature data, and specifically air temperature data over time, to look at patterns for a given location, for how temperature changes throughout the year, throughout the day, a given month, etc. So on a daily basis, we record our daily maximum and daily minimum temperature. If we subtract the two from each other, we get our daily range in temperature. We also have daily mean, and you'll see monthly mean and annual mean on this list too. Mean is just another word for average. So our daily average temperatures, our monthly and annual average temperatures. And then again, we have those ranges too. The daily range is just the maximum minus the minimum, and our annual temperature ranges too. We're going to see some trends here. For example, the largest annual temperature ranges tend to be near the poles, right? Not near the equator. The equator stays pretty consistent throughout the year, so it's going to have the smallest annual temperature range or difference throughout the year. An isotherm is a line on a map that connects all the different locations that have the same temperature. So we'll see in the next slide how that's helpful in determining what the temperature distributions are like, but also this temperature gradient. So how fast the temperature is changing over a given distance. Here are isotherms, and I do recommend that you check out the SMART figure. But we'll start with this 80 degrees here. So everywhere that's on this line, every location on this line is 80 degrees. So we connect all of those locations at 80 degrees and we get this line. And you notice that there has to be 80 somewhere between Little Rock, which is at 75, and Houston, which is at 83. So somewhere between that line we have an 80, and that's where it would be plotted based on where that 80 is actually taking place. But if you notice the distance between the 80 and the 70, we'd have to drive a long way in order to get from 80 to 70. So we say that has kind of a shallow gradient, not a significant gradient. In other words, it's not changing very much even though we're driving a long distance. But in other places, the gradient is a lot steeper between the 70 and 80 here. We call that a steeper gradient. And that idea should bring back memories of our topographic maps. The closer the lines are drawn to each other, the faster it's changing elevation over a given distance. So in this area over here near Gallup and Albuquerque, we don't have to drive as far in order to get a significant temperature change here between 70 degrees and 50 degrees. Our controls of temperature include what's being heated. For example, is it land or water? Land has what's called a lower specific heat, so it heats more rapidly. And water takes a lot of energy in order to change the temperature of water. And you might be familiar with this in your everyday experiences. Well, if you've ever tried to go swimming in, let's say, Lake Michigan in May or June, the water is still very cold. It hasn't been warm enough, long enough in order to heat up the water, even though the land is starting to warm up. And the opposite is also true. In October, the lake is still somewhat warm, even though it's gotten cold outside. So water is said to have a high specific heat, and that is defined as the amount of energy that you need to take 1 gram of water and raise it by 1 degree Celsius. So let's say you have a gram of water at 20 degrees. How much energy do you have to put in order to change that 1 gram of water to 21 degrees? And that's how we measure specific heat. And it turns out for water, it's really high. If you've ever gotten to your car in the summer and the metal belt buckle is really hot, but maybe you have a bottle of water that you left in the car too, and it's not nearly as hot as your belt buckle. Metal has a very low specific heat, so it does not take a lot of energy in order to change its temperature. But water is kind of famously known for its high specific heat. And how that plays out in our kind of weather data here is, in climate actually also, if we take a look off the coast of California here, the difference between the temperature of the land versus the water. So our land heats up a lot more easily than the water does. Smart Figure 16.30 gives us our monthly mean temperatures for 2 different locations. So why are they picking these two? Let's just look first on this map here to see what it's showing us. We have Vancouver, which is on the water, and Winnipeg, which is in the middle of the continent. but it's around the same latitude. Notice they picked cities that were around the same latitude. They should have the same sun angles, giving us the same amount of daylight during the day and the same angle the sun is striking the surface. So kind of all else being equal, what effect does Vancouver being on the water have versus Winnipeg? And we can see it's actually quite significant because water has high specific heat. It has this moderating effect on climate over time. So we see that Vancouver is more kind of stable throughout the year compared to its counterpart Winnipeg, which is a huge difference in the annual temperature between January and July, for example. That difference between January and July is very significant, where Vancouver, this marine kind of on the water city, is much more moderated by the fact that it's on the water. We see this effect in Europe too. I think sometimes I'm surprised to see what the latitudes are in certain European cities. I'm thinking like in the UK, for example, London is just a lot further north than I tend to think it is. But part of that is also because its climate is not typical of the latitude that it's in. Why? It's on the ocean. It's on the Atlantic Ocean and has those moderating effects of its climate due to the water. Altitude is another difference here. We have, in terms of explaining kind of what we're seeing in the trends throughout the year, if we have a town that's on the mountaintop, we're going to see it's a lot colder compared to something at about the same latitude that's not on a mountain. So higher altitudes have lower temperatures. We should know that, right? Thinking about those snow-capped mountains, as we go up a mountain, it gets colder. And our geographic position. If we have two coastal cities, we just talked about coasts being on the water having this moderating effect, but are we on the windward side or the leeward side? So our weather in the United States typically comes from the west and travels towards the east. So in Eureka, we have the weather dominating from the ocean and coming onto the land. So it receives the benefit of this moderating effect of the water that's sitting next to it. However, this leeward coast, New York City, since the weather is coming from the west and moving towards the east, it does not benefit from its weather coming from the ocean onshore. Its weather is coming from the continent and continuing past New York, then into the ocean. So we see a much more dramatic difference in temperatures in New York City compared to Eureka, which is on the windward side. Cloud cover also makes a difference. Remember, clouds have what's called a high albedo or reflectivity, so a lot of reflecting of the sun's energy back into space. Clouds have the effect of cooling the air during the day, but cloudiness will also kind of trap heat in at night. If you've ever been in a desert location, sometimes it's like super hot during the day, but then the temperatures just plummet at night because there's no clouds. So all of that heat that had accumulated during the day really easily escapes from the pavement and surfaces at night. So the same location now we're looking at for this particular graph, and on an overcast day, we have this moderating effect by the clouds, where on a clear day, we're going to heat more, but also give up that heat more readily. Temperature maps, again, we're going to look at some isotherms, places of equal temperature. We're looking at January and July data. So these 2 months are used because January is typically the coldest month in the northern hemisphere, at least represents a coldest time in several locations. And then July in the northern hemisphere is our summer, and it's just reversed in the southern hemisphere. So in January, it's their kind of extreme summer, and in July, that would be their extreme winter. So one pattern that we see when we plot global temperatures or temperature averages, we're looking just at January versus July, is that temperature decreases from the tropics. So our warmest areas tend to be in the tropics, and as you go towards the North Pole or towards the South Pole, our average temperatures decrease. That's a pattern I feel like we should relate to. Isotherms also show this latitudinal shift with the seasons. So remember that the sun is directly overhead on June 21st or 22nd, not at the equator, but at the Tropic of Cancer, which is 23.5 degrees north. So where we have kind of our warmest areas shifts throughout the year following where the sun is most directly striking the surface of the earth. And our warmest and coldest temperature extremes occur over land. And again, that's partly because, or largely because, our water has very high specific heat and is going to moderate changes in temperature that are experienced by the air. In the southern hemisphere, isotherms tend to be straighter and more stable. And the reason for that is there's just simply less land in the southern hemisphere compared to the northern hemisphere. I encourage you to take a look at the map in your book and really orient yourself with where the equator is, because I think it's sometimes surprising how little land there actually is in the southern hemisphere. So because it's mostly dominated by water, we have this moderating effect throughout the entire southern hemisphere versus the northern hemisphere, which contains a bulk of our continental mass. Here is our world mean or average sea level temperatures in January. Notice the warmest concentrations are occurring over land, typically. And this data here is in Celsius, but it's also reported in Fahrenheit. So depending on what you're more accustomed to understanding in terms of what this would feel like, negative 30 degrees Fahrenheit or negative 40 Celsius. So very cold here in January in the northern hemisphere, but we have this kind of steep gradient happening over the northern hemisphere here, and it becomes a shallower gradient as we get towards the equator. But notice in the southern hemisphere, we don't see those steep gradient lines of temperature. So because, again, there's very little, especially down in this region, continental mass, we see more spread out lines, meaning we have more stable or moderated temperature differences. And then here we are in July. Notice that the shift of the warmest temperatures has moved northward because the sun is now directly overhead, somewhere just south of 23.5 degrees because it's July. Again, we should see the trend where most of the intense warming is happening over areas that have land. And that is it for chapter 16.